Welcome to the Tactics Meeting, Episode 20, Chemical and Physical Properties of Oil. I'm your host, Dan Smiley, and here on the Tactics Meeting podcast, we talk to subject matter experts about oil spill response, tactics, and technology. But before we start, we're going to have a safety minute. And with us to help out is Amy Does from iWorkWise. Hi, Amy, and welcome to the program.
Hey, Dan, thank you.
The topic for today is eye protection. Amy, what do employees need to know?
I think the biggest thing here is what to choose, whether you need safety glasses, goggles, or a face shield. I see a lot of people in the field not making the choice, and it's real simple. Safety glasses are used for hard particles, and they're often impact rated, or they provide impact protection. Goggles are used for liquids. So liquid splash, safety glasses aren't enough. If you're working with a corrosive liquid that's going to burn your eyeballs out, basically you have to wear goggles. Face shields protect your face. They're not considered by OSHA to be eye protection. Things can get under them, and even now they're making some wraparounds. But basically, safety glasses for kind of standard things, goggles always for liquid hazards, and a face shield if you like your face.
Thank you, Amy, and thank you for helping to keep us safe.
You bet, Dan.
Well, thank you to Amy Does for that safety minute. And now let's get to this amazing podcast. It's time for the Tactics Meeting. Today, I have Dr. Tom Coolbaugh, who is now the program manager, facility manager at OMSET, works with Applied Resource Associates, formerly with ExxonMobile. Tom, welcome to the program.
Thank you. It's good to be here.
You recently retired from ExxonMobile. You've taught at the Northwest Area Spill Control course a number of times on the characteristics of oil's chemical properties, and that's what we're going to talk about today. But before we get to that, I'd like to ask you your oil spill story. How did you come to be in the oil spill response world? I'm guessing that this is not what you started out to do when you first went to college.
Yeah, you're exactly right. I have to admit, I didn't really know that it even existed. For college, I was a chemistry major. I knew I wanted to be in science in some way. So I was originally looking at chemistry or physics, and just chemistry sort of won out. I went to graduate school to get a PhD in chemistry. So I'm actually an organometallic chemist. So it's really around sort of the catalysis, the catalytic processes you can do with different chemicals. My PhD was actually looking at the time, this is in the early 80s when energy was the post-energy crisis. So there's still focus on synthetic oils, synthetic fuels. There's a process called the Fischer-Tropsch reaction where you can make synthetic fuels out of carbon monoxide and hydrogen and stuff like that. So that's really what I did my PhD in, not knowing ultimately what I'd do with that. Got a job in the chemical industry, which at the time I really wanted to be in the Northeast. I grew up in the Boston area. There aren't a lot of chemical companies in New England. So I managed to find a couple of places to work, but ultimately worked in doing polymers. I did adhesives for a British chemical company. I worked for a company that was called Uniroyal, which people may remember, used to make tires. Their product was the Tiger Paw, and they had some great advertisements for that. So I did modification of polymers, did things like that, and really tried to figure out how to make chemical or commercial products around it. But after doing that for a few years, it's like, okay, it's time to go find something that's a little bit more challenging. And I ended up getting a job with Mobil. So the Mobil Chemical Company had a research lab in Princeton, New Jersey, where I started as a bench chemist doing polymer science. And I figured, well, that's what I'm going to keep doing. Science is good. The lab is good. I kind of like the academic world of research. I had looked at doing a teaching job, had a position that was offered up in the Boston area, but ultimately decided industry is where I kind of wanted to go. It just seemed like it was more applied, more focused. Hopefully you could do something that added to something, not just sort of the knowledge aspect, but the actual hands-on doing it. So mobile started in 1988, and you may have heard of a spill that happened in 1989 called the Exxon Valdez, not the Mobil Valdez.
I've vaguely heard of it.
Yeah, maybe. It kind of created an industry for a lot of people. But at the time, I was in the chemical company. So, and I was not Exxon. So it really wasn't that much on my radar. I was in New Jersey. That was Alaska. Certainly there was a lot of imagery around it, but it was in a different world. It was of interest, of course, but not really from a career perspective, because I think a research chemist in a chemical company in New Jersey is worlds away. So I ended up working again for Mobil Chemical for quite a while, but 4 years into it, I was asked if I wanted to do a planning position, just a sort of an expansion of roles to learn something different about the company. And the one thing I will say, and this sort of factors into how I got into oil spill response, is never say no when people ask you, do you want to try something new? So this was to do planning. I was going to be embedded within the finance department of what was called the Chemical Products Division of Mobil Chemical. They had an office building in Somerset, New Jersey. I thought, well, okay, I can give that a try. So I figured it would be a 2-year sort of rotational developmental assignment. That's something that Mobil, Exxon, other companies do that. It's not atypical. So I was surrounded by sort of financial management MBAs, looking at doing a capital evaluation of the returns on investment for capital projects, things like that. So I picked up some different skills, but ended up being in that role for 5 years for a variety of reasons. At the time, the companies were looking at how to sort of reduce some of their middle management, so you get sort of locked in place for a while. But ultimately, I got back into the research setting. My group that I had left in Princeton moved up to Edison, New Jersey, to a manufacturing site, and they put me back in that role as the manager of the group. So I ended up managing a research lab. About that time, not that long after, Exxon and Mobil merged. So all of a sudden, the Exxon Valdez, which was something a little bit further removed, became part of the heritage of ExxonMobil. So it was kind of different. Now it's a little bit more on my radar, but I was still in the research and engineering world and moved over to what ExxonMobil still has. It's the Corporate Strategic Research Labs in Clinton, New Jersey, Annandale, New Jersey. It's not that far from where I am now. And I was at the section head for polymer science, which again, so it's science. But the person who was in a role around oil spill response technology was in the office in our Fairfax facility down in Virginia. And he knew that they had a hole in their spill response technology around chemistry. He came from the EPA. He was more of a biological background. They wanted somebody with chemistry. So he came up and talked to me in about 2006 and said, would you be interested in this kind of a role? And I said, first of all, I didn't know you guys existed. I didn't know there was a corporate, an ExxonMobil response technology group that supported science and technology in being prepared for a spill response. So I just didn't know that existed. And I thought, well, it makes sense because that's part of the heritage. Oil spills do happen, and being ready for them and being able to respond to them is certainly important. I said, sure, I'd be glad to consider it. And he said, okay, it's like February at that point. We'll be back at the end of the year because we're really looking at what we need to do for the budget and everything else. Well, March of that same year, I got a call from his boss saying, how about now? I said, fine. And again,
what had happened that sped that up?
I have no idea other than looking at a staff. It could just be that they realized, hey, we have funding to do it right now. If we wait, we might lose that funding for that position. So let's fill it. We've got a head count that we can add. Let's do it. And here's a person who actually I had worked with his manager in a different role back up in the Clinton, New Jersey facility. So at least she knew who I was. So I wasn't totally unknown. He thought I was okay from a science standpoint. So it just sort of came together. And I said, there's no reason I should say no. I'd be happy to do it. It means I have to move from New Jersey down to Virginia. So around the DC area. But I'm open to that. I'd worked in New Jersey for 19 years, 4 different positions at different locations. So I'd moved, but never had to actually physically relocate. So again, don't say no. I've worked with somebody before who did say no for a different position, and the management came back and said, okay, realize the train comes by once.
Right.
If
We're
you
never
get
going to
on,
ask you again.
Exactly. If you don't get on, it's not coming back. So I've done a lot of recruiting, and I tell people that be open-minded. The one thing you'll realize is you'll learn something about that position. You may like it, love it, whatever. If you hate it, you find out there's something I know I don't want to do. So then you move on from a position of at least informed opinion. So I did say, yeah, I'd be happy to. It's chemistry. It's around really the science of spill response. It's something the company values. And I thought I will take it. So that's when I started in 2007, not knowing exactly what it was. But I got to work with some great people within ExxonMobil who'd actually been around since the Valdez. We had a lot of history. We had a lot of files about what was and what worked, what didn't. And they had a need for, again, that sort of the chemical side of the response to spills on open water, out in the open ocean. Because again, the Valdez sort of showed the limitations of some of the technologies. And the chemistry at the time was really looking at was dispersants, which now everybody has an opinion about. But back in 2007, when I took the position, I thought, well, no, it's just a chemical countermeasure that I can bring some bearing to because at least I understand chemistry.
Did the dispersants already exist, or did you help develop the dispersants themselves?
The dispersants had actually been around since the late 60s, early 70s. The Exxon products that became the Corexit product lines were really developed around, again, the late 60s, early 70s by Exxon researchers that were really looking at how to make things as effectively as possible. They've improved over the years. The challenge we had is people still think about the Torrey Canyon spill response off the UK back in, 67, 68. There were materials that were used to try to take the oil off the water surface and disperse them into the water column. But they were really chemical degreasers. They were highly toxic, aromatic polar compounds that the aquatic life did not like. So it really gave dispersants a bad name for decades. But in the meantime, formulations of, let's say, the Corexit and other types of what I will call earlier versions of the modern products looked at how to make things that were less toxic, more effective. You could certainly use less of it, and you really wouldn't harm things intentionally or unintentionally. You at least try to make something better. So at that point, yes, they had been around, and I got to work with a guy named Dick Lassard, who was one of the original people who was really around the science and technology of that. So he was still there as a consultant, so that was really good. And it sort of got me up to speed. And for 3 years, was really out there working with people like Marine Spill Response Corporation, coming out to Seattle to do training for the tribal groups along the Pacific coast, doing things like the Northwest Oil Spill Control course. And it really opened my eyes to what it really is. And I ended up giving a lot of talks about what the dispersant technology is, what it is, what it isn't. It's not a panacea. It's just another technology, what we always talk about. It's another tool in the toolbox. We always say, and this is easy to say, the best spill is the one that doesn't happen, but we know they do happen. And if you can pick it up and put it back in the box, the tank, whatever, that's ideal too. But we know that in the open ocean, let's say 50 miles offshore, in whatever sea conditions there might be, the chance of picking up 100% of that floating oil is essentially zero. At best, you can say whether it's 5%, 10%, 15%, it's a minor component. So what else can actually treat it in a way that helps the environment deal with it? And dispersants are actually a reasonable approach to that. But, we can talk about how they get approved and all that, but they have to be commercially available, modern materials that have low toxicity. And the materials that are currently used are things that are actually found in commercial products that we get exposed to on a relatively daily basis, whether it's hand lotions, skin creams, even gelatins, food products. These are surfactant components, 3 of which are, I'll say they're called non-ionics, and there's one that's called an anionic. And the anionic surfactant is called sodium dialkyl sulfosuccinate. It gets abbreviated as DOS, D-O-S-S. But it's in a commercial laxative that people take internally, willingly. So I'm personally not really too worried about the toxicity of the component. performance. It's how do you do something effectively with a spill response? Because in my opinion, once it washes up on shore, especially a sensitive shoreline area, it's a protracted cleanup now. It's not just a spill response. So for 3 years, I had the luxury of just focusing on the science, going out and talking to people, working with the American Petroleum Institute and IPCA and other international organizations on how these things get approved. And then 2010 happened. And that sort of changed the focus around the science and use of dispersants significantly. As you know, Deepwater Horizon raised a lot of attention to something that people hadn't really paid that much attention to before. So I would say before 2010, people didn't know what dispersants were. Following 2010, everybody had an opinion. And it wasn't necessarily based on science. And so my predecessor in the group that I was in, Jim Clark, he had worked with the EPA. He'd been with ExxonMobile for a while, then he did retire. He said, your career has just changed because now you're one of the few people around the world who talk about the science of dispersant use during oil spill response. So if you ask me how I got to where I am now, the career path to that is kind of ill-defined. And I do tell people that coming out of college or graduate school, whatever you think you're going to be doing, 5 years from now, you're probably going to be doing something different, especially if you're in the world of industry, because again, industry moves to where it has to. And I was lucky enough to be in those positions where somebody asked, do you want to try this? Do you want to try that? And it actually added to what I did. Even when I took that first position in the financial planning, at that point it was Mobile, supported me getting a degree in management of technology. So I've got a BA in chemistry, a Bachelor of Arts. It was a liberal arts college. Then I have a PhD in chemistry. And then I have a master's. So I have a BA, a PhD, and a master's in that order. And the master's is in technology management from what's now New York University. So it's, you never know, but take advantage, be open-minded. And this is the best job I ever had. The oil spill response I spent 32 years at ExxonMobile. I retired last July after 32 and a half years. The oil spill response world, the community, was really the best job I've ever had because you get to see people like yourself and others on a regular basis in different settings. Hopefully it's not during an emergency. Hopefully it's during a drill, an exercise training. But if there is a real event, we know that it's all hands on deck and it's a community that pulls together. So it's been phenomenal. I really have no complaints with that, but it's a slightly different entree into it than maybe somebody like Ed Owens or whoever else, Elliot Taylor. It's just, you never know. Tim Medwed, who's still one of my colleagues down at ExxonMobil, he comes to it from an environmental science standpoint. I came from the chemistry standpoint, working with people like MSRC up in Port Angeles, Washington. It's just the hands-on side too. Mine was always more of the theoretical regulatory approval process, but during, let's say, a spill response exercise using ICS or internationally IMS, the Incident Management System, I was always in the planning section in the environmental unit as the technical specialist for dispersant use, which is kind of focused. And it hopefully only has a focus for, let's say, 72 hours for a single release. But something like a Deepwater Horizon, it was a topic for the entire 80 plus days. And again, I had the good fortune to have been part of those discussions, both during and after, and even still. So again, it's kind of a circuitous route, but that's how I got here.
Yeah, I got here by driving ships, and I was gone all the time. And in an effort to stay married, I took a job with Clean Sound Cooperative, which was a local co-op in Puget Sound, because they had a job for a licensed captain for an oil spill vessel in Bellingham, the Western Gull, which was a 10-minute walk from my house. So it's like, okay, great. I don't know anything about oil spill response, but they've got this cute little coastal skimmer I can drive, and I'll do that. And it completely changed my path. Now I design drills and do other stuff. It didn't work on the stay married side, but it
Okay.
did change the trajectory of my career into something that I have really, really enjoyed.
Yeah.
So let's talk about oil. The class that you gave at the Northwest Area Spill Control course on the property of oil that I sat through several years ago was great. And I'm excited to be able to talk about here today because I think a lot of even oil spill responders today don't get enough training, enough education on what oil really is. What are the chemical and physical properties of oil? Because when we talk about crude oil, we say it as if it is a single thing.
Yep.
But it's not a single thing. So could you start by giving us a definition of, what is oil?
Okay.
That may not be easy, but I'll toss it to you anyway.
Oh, it's in some ways it's easy because you say, well, there's not one answer to that. But you're right, exactly right. So, there are safety data sheets for everything that we deal with from a chemical safety standpoint. And you can actually get the SDS for crude oil. And it's kind of silly because there is no such product that is a single product of crude oil. It's a very complex mixture of all sorts of different chemical compounds. In fact, if you do a gas chromatograph or a mass spectrum of it, you'll see that it's composed of thousands of different chemical compounds. And even when you have an ExxonMobile or other companies who do analyses and refining of crude oil, they basically use models that what they call structured ordered lumping and other things to try to look at functionality and classes because they can't deal with each individual component. It's just there are too many. A fresh oil, what you might call a live oil, when it comes out of the ground, it's got all sorts of stuff in it that gases and other things. It's never quite this pure material. So it has a lot of high volatility, low molecular weight, small molecules that vaporize fairly quickly. And if you've ever been around fresh crude oil, it smells. And depending on whether it has sulfur compounds or other things, it can be what's either called sour or sweet. Sometimes it really stinks because of the sulfur compounds. Other times it almost looks like something you put directly in your car, depending on how viscous it is, how pure it is. So it's got lots of compounds, and we do have sort of a bunch of different ways of categorizing it. There's something called SARA analyses. That's SARA. So it's saturates, aromatics, resins, and asphaltenes. Those are just four sort of representative categories of the components that are in there that help us understand how it will behave under different conditions. So it's not necessarily all that quantitative. It's again, it gives us an idea where you can say it's 25, 25, 25, 25% of all of those, or is it 10, 10, 40, 40? It'll tell us something about how it'll behave. Along with that, then, is how thick is it? How viscous is it? There are some that are very thin, almost like water. There are other ones that are like honey, just as it comes out of the ground. So they're always different. And even if you go to a particular place in the world, get oil, and then say, okay, now I know what it is. Go back there 20 years, and it will be different because different components that you're taking are different components within what you're taking out either deplete, they move, they volatilize. So the oil you took out from Alaska back in 1960 is totally different from what's coming out of there today. Other times, the oils that we collect are blended because there are several wells that feed into a pipeline, and depending on what's being fed into that pipeline, they can differ also. So it's kind of a snapshot in time of what they are. So we just deal with what's its viscosity, what kind of components does it have in it, how does it behave under different conditions, even temperature, because they have what are called pour points. There are some things that as you cool them down, they just get more viscous, they'll get thicker. If you take honey and put it in the freezer, it almost solidifies. And that is a point where we call that the pour point. If it no longer moves, if you try to pour it, you've gone below its pour point. And that has a lot to do then with how we deal with it if it gets spilled. If you spill something in Alaska, it could be totally different from something you might spill in Singapore just because of the temperature of the water. And if the water temperature is below the pour point of the stuff that gets spilled, it more or less solidifies. And that then changes what you can do with it. If it's solid, you can't really skim it. You can't pick it up with some sort of a mechanical means. You'd almost need a shovel or a pitchfork. So understanding what those are, and those can be, you can learn a lot by what are the saturated components, the sort of the waxy materials that may, like a candle, things that will solidify at a certain temperature. If you heat up a candle wax, it melts at a certain temperature. And that's really what happens when you go below a pour point. There was a spill off the coast of Western Australia just before the Deepwater Horizon, the Montara well. It was more or less what we'd call a condensate, but it was very waxy. So during the day, it was fine from a standpoint of skimming it or dispersing it. But at night, when it didn't have the sun on it, it solidified into this waxy material. Sun would come out, it would melt again. So the more we know about the characteristics, it just helps us understand what we can do with it. So when somebody tells you, yeah, I've worked with crude oil before, I know exactly what that is. It's like, no. And there are other things like what we call diluted bitumens or dilbits that are very, very heavy materials that sometimes they're called oil sands or other types of things that are very almost tarry, that to be able to deal with it or pump it, you add a solvent to it to make it much more fluid and mobile so you can put it in a pipeline or something. So those are even different. The other main characteristic, along with viscosity, and I should say that it was the density. So if it's really light, it floats really well. It's less than the density of water. That makes it easier. There are other ones that we deal with that sometimes have densities on the order of, let's say, 1.03, which would be 3% heavier than fresh water, which means they sink. And a sunken oil is a completely different animal to have to deal with. There was a spill on the Delaware River a long time ago when a vessel called the Athos 1 had a hole torn into its hull, and it dumped a whole bunch of sort of like asphalt-like material into the Delaware River. And the hardest part is to find it. And then once you find it, how do you get it out? So from a spill responder, that can be a real challenge. So again, you have all these different characteristics, and sometimes we try to simplify how we characterize it. So the SARA analysis, that's one thing. The density, and then we can turn that into something that we call the API gravity, which it's sort of the inverse of, its density. So a higher API number is a less dense material. So an API 50 is kind of more like a gasoline type material. And if you get down to an API of, let's say, if it's 10, that's really, really thick, viscous, heavy stuff. So 10 to 20 heavy, 20 to, let's say, 35 sort of medium crude, and then above 35 and above what you might call a lighter crude. And those help us understand from a spill response standpoint, can we skim it? Can we disperse it? Can we deal with it? Where's it going to go? So it's such a complex mix that we've tried to simplify how we characterize it. But as a chemist, it's always good to see what the gas chromatogram traces look like, so we kind of know what we're looking at.
Washington has some new regulations that go around oils that have the potential to become non-floating, is the way they put that. And one of the requirements that we have is to do an analysis or an evaluation. Analysis is probably too scientific a term for what we're going to actually be doing. But to evaluate within an hour its potential to become non-floating. And we look at an SDS, and it may have a specific gravity, and it may not, or it may give us a range on the specific gravity. Mm-hmm. And for those who maybe need a refresher, a specific gravity is the weight of a material relative to water, relative to fresh water. We give fresh water a specific gravity of 1.
Yep.
And materials that have a specific gravity that are greater than 1 are heavier and will sink. And those that have a specific gravity of less than 1 are lighter and will float. But as we started by talking out, crude oil is not one thing. And there are, what did you say, hundreds or thousands of chemicals? Thousands.
Oh, yeah, thousands.
Thousands. So some of these are are, high vapor pressure, volatile products that are not going to stick around for very long, right? So
Yep.
as we spill it, maybe that initial product has a specific gravity of, 96, right?
Yes. Okay.
But
Yep.
but what's it going to be 5 hours from now,
Mhm.
10 hours from now? And so how would you think we go about doing this evaluation and using specific gravity and API gravity as part of our calculation? And not all SDSs have an API gravity in
No, they
them.
don't.
And a lot of the SDSs, as you point out, for a crude oil, let's face it, they're kind of useless.
I agree.
So what do you think?
Okay. Well, so there are a number of things that we do to at least help understand. And there are some models that have been developed that help understand what we'll call it the weathering of the oil. So once it gets released into the environment, it is now undergoing all sorts of different processes. If let's just say you spilled it on a sunny parking lot. So like you pointed out, there's some volatile components. Those lighter ends will evaporate. And as they evaporate, they are the molecular components that actually are physically lighter. So they evaporate, which means your average density is getting heavier. So if you're at 0.96 and you lost 20% of your light components, it's very possible you're going to be 1 or above within a matter of time. In a parking lot with the sun on it, that could be pretty fast. If you're in a place where you spill it on the water, in the cold, in the dark, whatever, that may take longer. But NOAA, so the National Oceanic and Atmospheric Administration, has a model that we particularly look at that's called ADIOS that can do some modeling of, I'll say, surrogates of oils that hopefully are close to the one that got spilled. We won't always have the exact one that you might have spilled, but if you know some of the characteristics that might be given on the SDS, but also might be available from the company who was transporting it, that have a little bit more of the characteristics, you can pick a surrogate that's close, feed it into these models, give it the temperature, give it, again, what kind of wind speed, things like that, and then it can give you a time profile that shows what's happening to the density and the volume with time, and also the viscosity. So all those things are changing. And you may have a matter of 24 hours, you might have 72 hours, you might have less as you start losing things that are right on that borderline. So at least from a response standpoint, especially if you've done exercises for an oil like the one that might spill in that particular environment, hopefully you have that answer, let's say the 80% solution ahead of time, so you know what resources, who do you need, what equipment, what do you have to do, and what's your timing to do that. So models are good. People are critical of me occasionally because I'll say this one thing that says all models are wrong, some are useful. But it's really, they're useful to the extent that people understand what their limitations are. So as long as you're using it as a guideline, I think they're really very useful. But don't use that as the absolute answer, because you know what's happening. Spills are all unique. So whatever you plan for in your exercise, the reality is going to be different. The other problem you might have, especially in, let's say, a riverine environment, or like an open ocean close to the Mississippi River, where there's a lot of sediment in the water, oil and sediment tend to like each other. So they will absorb onto the surface of the sediment particles. And just by virtue of doing that, you could easily increase the density of that oil with that other component, so it will sink. It could be for good or bad. In the cases where there's a lot of sort of active turnover of the water and there's some very fine sediments, that can actually help what we call microbial biodegradation of the oil, because it's a material that has energy in it, and there's always some bug out there that can find some way to generate energy by consuming it. But there are all sorts of different weathering processes. So, again, we talked about evaporation, talked about sedimentation. There's also emulsification. Some oils really absorb water into their oil matrix, and they start to increase their volume. They increase their viscosity significantly. Their density, it depends on what they were. It might become more dense than it was. But again, it's this thick stuff that's very tough to deal with. But it's that those other processes where you're either losing the lighter end or adding something heavier.
Do
that
the
can
water
make you-
molecules bond to the?
They actually, so an emulsion, if you think of, so we're talking about oil and water. So there's something called an oil in water emulsion. That's something like a mayonnaise, or there's a water in oil emulsion. That's probably the same thing. That's the mayonnaise. But if you think of that continuous phase, so take oil, you've got this volume of oil, water droplets make their way into the oil. They still stay as separate droplets, but they start changing the affinity of the different molecules together. So the waters start changing the interactions. It starts building, first of all, volume. You can make some emulsions that are more than 50% water. So if you had a gallon of oil, now all of a sudden you have 2 gallons of emulsified oil. And it still looks like oil. You still have to do something with it, but now it's 50% water. And at the same time, it may have gone from being that watery viscosity, something that we would call, let's say 10 centipoise. It's just a measure of unit of viscosity, but very fluid. And it might be 1,000 times more viscous as it started getting this water mixed into it. That's where, again, looking at something like if you have oil and water and you emulsify that into, let's say mayonnaise, and you've added some other, like an egg in there to bind it, whatever you might want to do, you know that mayonnaise has a very much higher viscosity than either the water or the oil that went into it. And it's that kind of characteristic and process. So emulsification is a challenge also. But all these different weathering processes, but the ones that really change the density are the evaporation, sedimentation. There may be other processes that go on, like photo-oxidation and some other things, but it's those other ones that are really the major, the bulk changes in the product characteristics of the oil. Because if you evaporate 30% of that lighter end, you've totally changed what you're looking at. So spill response, it's a matter of get there as quickly as you can before you lose control of what it's going to do. Unfortunately, we're in a world now where most people think that spills are like the Deepwater Horizon, where again, you have almost 3 months to deal with it, and it's fresh oil every day. Fortunately, that's not the case. Unfortunately, there are still spills, but they're usually small, single releases, and you've got a time window to do something with it because it's changing right before your eyes.
So what is photo-oxidation? What is that process?
Okay, so when you're out in the sun, just think about the fact that put your hand out in the sun and you will get some sort of a sensitivity to it because sun has energy. The sunlight, all light, it will interact with what it strikes. In the case of your skin, the pigments, it will do something. In the case of oil, there are some reactive components in there that will gain energy from the light that hits it. It will then move into some sort of, I'll call it just a reactive state. It doesn't really matter what that is. You can end up with an active species containing oxygen or something else, and then it reacts further. And a lot of times that means that it reacts with other molecules. You get build of molecular weight. Could mean that you also make other molecules that are totally different than what was in the oil to begin with, because there's always air around. Air is an oxidizer. That's why oxygen, oxidize, that's why it's called that. But it's always there, and there are certain conditions under which it's very reactive. And if you've got a very thin layer of, let's say, oil on a water surface, let's say in the Gulf of Mexico, and it's seeing a lot of sunlight, there's a lot of photo-oxidation that can happen fairly quickly. It can build sort of resinous materials, but there's been work done by Woods Hole and others that have indicated that it can also change the toxicity of the oil itself. Crude oil has toxicity, there's no doubt about that. But sometimes these oxidized species can be even more of a sensitizer to the organisms that are in the water. So again, time is important to get these things out of the environment before these transformations go on that will go on. What the extent is, to me, it's still a little bit of an open question. National Academy's study was done that finished up last year. It was a 2020 publication on the use of dispersants for chemical dispersants for oil spill response. And there was a fair amount of discussion about photo-oxidation and how that sort of changes some of the toxicities associated with, I'll say, what dispersants and other things do to the oil. But it's still a little bit of an open question, I think. There's a lot of academic research that would indicate it's a significant problem. But to me, it's an ongoing discussion. But photooxidation, just think of if you put paint out in the sun, like especially red, it will fade. And that's photooxidation effects from just the sunlight. So it's a chemical reaction.
So the chemical reaction that's taking place that has the potential to make the material more toxic, is it in quantities that we need to think about from a responder safety, personal protective equipment, respiratory protection perspective, or is it in much smaller quantities than that?
It's much smaller, and it's the toxicity for the aquatic organisms. Okay. So if we make something that's relatively toxic to a certain life stage of a larval fish, the sensitivity can be pretty high. For the human responders, that's typically, in my opinion, not an issue. The ones that I think are the bigger issues are the exposure to the volatile components that are coming off of the fresh spilled oil. And that was part of what we saw during Deepwater Horizon and some of the others. If you spill oil, you can smell it. And for some people, that what you're smelling, they can be sensitive to. And there could be aromatic compounds, there could be benzene, there could be other materials that you do not want to breathe in. So if you're an initial first responder, depending on what your sensors might say, whether you're checking for hydrocarbons, different components, if it's above a certain level, the Occupational and Safety Health Administration requirements would say above a certain threshold, either get out of the environment or you have to wear some sort of respiratory protection, which if you're out in the middle of the summer, that can be pretty uncomfortable. But yes, we have to understand what the air quality is, but it's those lighter ends of fresh oil that to me are the bigger issues around responder safety. And if we can prevent that from volatilizing in the first place, if we can control it either at the source, if it's a subsea blowout, can we do something else to prevent it from showing up where the responders are? That can be a plus. And that's something that has come up over the last few years, that if you prevent it from surfacing as a slick, you can actually have some protective effect for the people who are actually trying to either stop the well or just pick up what's out there.
Well, how is API gravity calculated? So you gave kind of a definition or an idea of, based on what the API gravity is, what is its viscosity, but what goes into developing an API gravity for a specific product?
So the whole point we talked about before, that water, the specific gravity is 1.0. You could have a crude oil that might be, let's say, 1.03. You could have a crude oil that might be 0.91. So if you told somebody, okay, what's the difference between a crude oil at 0.91 and 0.93? That's not much of a difference. So when you're trying to talk to the response community, the regulators, it's kind of a challenge to get a feel for that. Why should I care about a 0.94 versus a 0.98? Those are essentially the same number. So the API gravity was defined in a way to sort of spread that out and give you a scale that's broader. And, I've gone back to look at this from time to time to see how it originated, but it's a simple equation. I'm going to read it to you. It's 141.5 divided by the specific gravity. So if that specific gravity is 1, 141.5 divided by 1 is 141.5. Then subtract 131.5. So if it were a specific gravity of 1, like water, its API gravity is 10. So 1 turns into 10. So it's a number that people can get a better feel for. But as you go to lower numbers, so the 141.5 divided by a smaller number means you're getting a higher API number. And that's where you can start to get that scale from 10 to 50 instead of 1 to 0.9. So it really gives us a better understanding. Although the discontinuity a little bit is the higher the number, the less viscous, the less dense. It seems counterintuitive, but that was the whole point, to spread it out where you could say, again, 10 to, let's say, 28, 25, 25 to 35, and 35 to 50, as opposed to, again, those little gradations of 0.91 to 0.93. It was to spread it out to be able to make us understand, more macro scale of the differences. So it seems a little bit arbitrary, and I've tried to go back, and I just have never seen why they came up with it. But you can go look up the history. It was done a while ago, but that's the equation. It's just 141.5 divided by the specific gravity, and that number then subtract 131.5. It's easy. It seems arbitrary, but it is a well adapted and accepted scale.
Well, that's the important part, right? We're all
Yes.
using it. It's kind of like the incident command system. Well,
Oh, yeah.
its strength is that we've all agreed to do it.
You know exactly when somebody says you got to go do this, you know exactly what they're saying. Okay, did you do your 214? You know, it's like, okay, yeah.
Right. It may not be the best system that could possibly be invented, but it works, and we've all agreed. So,
And it's
good enough.
There are so many things like that it just becomes a de facto standard that we understand.
Yeah, I think Winston Churchill said that democracy was the worst form of government on earth, except for every other form of government on earth. Good enough, right? We're doing it. So
I've also heard the thing that says one thing about, let's say, several individuals in particular. It's just they will get the right answer after they do all the wrong things first. And sometimes that's the way we work. We learn by those mistakes, but ultimately we get there.
that's right. So we've talked about evaporation, emulsification. How about dissolution?
Okay.
What do we mean by that?
So there are some things that dissolve in others. So if you have ethanol, so we know what ethanol is, it's infinitely miscible with water. So those things you just mix together as much as you want. Like if you look at vodka versus, whatever, you can get all sorts of ranges. It's just, they mix. Other things much less so. And let's say in crude oil, most crude oil, you'll see it floats. It does not mix well with water. It's like oil and water in a salad dressing. They separate. But there are some components within it that do dissolve. So in the case of, let's say, the Deepwater Horizon spill, Macondo, it came up through 5,000 feet of seawater. By the time it got to the top, there were some fractions that never made it because they dissolved in the water as it rose. They tend to be the lower molecular weight materials. They tend to be what we call the polar materials. So they may have oxygens associated with them, or nitrogens or sulfurs, or they may be aromatic materials like a benzene. It's a cyclic six-membered ring. It's pretty well dissolved in water. So the good thing is, if you're a responder during Macondo, as the oil came through the water, if it wasn't collected down at the wellhead, the benzene was gone. It went into the water column, it dissolved, it never made it up. But the larger, I'll say more aliphatic, so the hydrocarbons, carbon and hydrogen, like let's say a cyclohexane, something that doesn't have that, I'll call aromatic component, those will rise. So it segregates based on its solubility in the liquid that it's in. The other thing that was good for Macondo, because it was so deep, there was a large gas component to that well release. And gas, I mean methane and propane, methane, ethane, propane, lighter molecules, those dissolved into the water column as well. Because if you were up at the top and all that gas showed up, there definitely could have been an explosion or fire hazard, much more so than what actually rose. So dissolution, just because of the way it works and the exposure to the water, you do strip out that some of those lighter members and some of the more toxic components. So in that way, it's good. But in general, most crude oil components have very, very low solubilities. So they will show up somewhere.
So how does the chemical component of a particular crude oil relate to your ability to use in situ burning as a response tactic?
Okay. So in situ burning, it just means burning in place, but we had to give it sort of a Latin name, so that's why it's called in situ burning. It is there are a couple of response techniques that have, I'll say, an advantage, especially if you're in a remote location with very little infrastructure. You don't put it in a tank, cart it away, and do something with that waste. That would, again, be the best thing if we could collect it. But again, if you're in a remote place and you can't store it, if we can do something like burn it, we've taken it off the water surface, we've transported it into the air column, but if we've got a very efficient burn, it'll primarily be carbon dioxide and water. We know that that's not always the case because you see the black smoke that goes along with it. It's not complete combustion, but most of it has burned. So the good thing is, again, if you're far away from human populations, if you're far away from sensitive areas, and again, if you don't have the ability to collect it and do something with it, in situ burning turned out during Deepwater Horizon to be a pretty effective way to deal with oil floating on the surface. There were, 412 burns, something along that line. Sometimes thousands of barrels burned in one day, which sounds horrific, but the alternative of that washing up in the sensitive shorelines of Louisiana could have been worse. But you can't just light anything. If you tried to go out and start an asphalt road on fire, it's probably not going to work, at least in our sort of time scale, because the things that burn, like if you think of gasoline, people think gasoline burns. It's the vapor above the gasoline that burns. You have to get that vapor to form. Otherwise, we've talked about, or we mentioned earlier when we were talking about explosive limits. There are times when either there's too much oxygen or too little oxygen. And if it's a pure liquid, you can't burn that. It has to be at a point where you have oxygen coming into it, have an ignition source, and then you burn the vapor. And then the vapor just keeps on feeding from the liquid. But in the case of an in situ burn on water, that water is a huge heat sink. So as we talked about, you need the fuel, you need the oxygen, but then you also have to have the ability to ignite it. And if things are below a certain temperature, they're very difficult to light. So oil on water at a certain thickness, it stays too cold for too long to really start it. So there's a minimum thickness you really need for oil to be. So it sort of insulates the top layer from the water layer. You can get the vaporization of that top layer to the point where you can light it. And then once you've done that, chances are you can sustain that for a given length. But it's that it needs to be on the order of 1 to 3 millimeters thick to start it. So once you get back down to 1 millimeter thick, it cools down too quickly and it'll extinguish. So there was a lot of work done during Deepwater Horizon to figure out how to really make these thicker films of oil so we could burn them fairly effectively. Most oils, as it turns out, given enough thickness and enough time with a flame, we can get enough volatility to actually start it on fire. You can't just throw a match at it and it'll start. People tend to think that crude oil will just explode into flames. It's not a gas. It doesn't have that kind of volatility. It's not that easy. But for most cases, it's been possible to burn. Even on land in the cold, if there's an on land up in the Arctic where you can't get people in, you can't get heavy equipment in, an in situ burn may be the right thing to do. But all you have to do is be able to give it enough heat source to cause the vaporization. And I think they were using just plastic jugs with gasoline or diesel along with a marine flare, and that was enough to get it started pretty easily. But the Macondo oil, the Deepwater Horizon oil, was relatively light, so it had some vapor pressure to it to start with. The other challenge, we talked about emulsification. So as you start getting water incorporated into the oil, if you get about above, say, 30 to 50% water content in that mix, so it becomes that what we call a mousse, it starts to look like chocolate pudding or something like that, it becomes harder to ignite those as well. Although some work that the Bureau of Safety and Environmental Enforcement, BSEE, has been doing, even starting in situ burns with emulsified oils, it can work as well. So I think we're expanding the envelope on what we can actually burn. Big challenge, though, is that black smoke. It's optically, first of all, it looks bad. There isn't necessarily a lot of toxicity. We do monitor the particulate components that make up the soot, because there's a health effect if the particle size gets down below 5 microns or so. It's that, or 10, I guess. The sub 10 microns become something, if you inhale it, it's very difficult for your lungs to clear it out. So there is a health component associated with that. But generally, it's not an issue. It's more the concern people have when they see this black, sooty smoke plume. So there's work that's been done in trying to increase the efficiency of the burns so there's no black smoke. And again, whether it's been ExxonMobile, API, BSEE, there has been work to show you can pump air in, and you can get a much more efficient burn, and the black smoke goes away. So, and you can add other components that help oxidize it further. The problem is that crude oil, I'll say it's deficient in its oxygen content. It doesn't have a lot of oxygen in the molecules. It's mostly carbon and hydrogen. And it's not necessarily at the right ratio of carbon and hydrogen to make a very efficient or completely efficient formation of CO2 and water when you start to burn it. There's something called stoichiometry, which is not a word even chemists are very happy with. It's not our favorite concept, but no, you have to have a balance of all the things going in. The left, what we call the left side of the equation, and what comes out of the right side of the equation. You want them to be the same ratio or the same numbers, the ratios change. And the stoichiometry of just burning crude oil with just air from the atmosphere is not always perfect. And that's why we get this black soot.
Do you do any burning tests at OMSET in the tank?
No, they did a long time ago, but they actually just use natural gas as a surrogate for it. We are in New Jersey, which you may know is what's called a non-attainment zone. So burning things is very heavily regulated. We're in a neighborhood. We're in the middle of a naval weapons station. We can see Manhattan. This would be a problem. There were places, there are places like the cold weather, the lab Krell up in New Hampshire. They do burning. There is a place up in Fairbanks, Alaska, Poker Flats, where they've done some burning there. The Coast Guard had a facility, I think, in, I'll say Mississippi, but that has since been closed. So there are CEDRA research facility in France, has what they call a burn bench. So they do it in a laboratory setting, but just very small scale. So there are some places that do it, just we don't here. We've been asked. We've also been asked if we can do sort of microbial work. It's like, no, so you can't see it, but behind me is this tank that's 200 meters long by 20 meters wide by, let's say, 3 meters deep. So it's 10 million liters of seawater. It's chlorinated because the last thing we want is to have 10 million liters of slimy green water. So no, we can't do microbial work in this tank. I'm hoping that we will have a smaller tank that we can do some work like that, because we've been asked by some universities, especially after the Gulf of Mexico Research Initiative, the $500 million that BP paid to support academic research in the Gulf of Mexico. A lot of that was around biological evaluation of what happens to crude oil in the environment. And we've been asked if we can do that here. And it's like, I hope so, just not yet.
So what is the chemical difference? I don't have an SDS for it in front of me, but I'm going to be doing a drill here in a few months where the spilled product is renewable diesel.
Okay.
Which I think is another name for biodiesel.
Biodiesel, yeah.
But yeah, which so and still regulated.
Yep.
So what is the difference between a biodiesel and petroleum hydrocarbon?
Okay, so the diesel from the petroleum, we've got a refinery that goes through and by distillation, catalytic processes, other things, can break down a barrel of crude oil into a whole bunch of different components, whether it's gasoline, whether it's aviation fuel, whether it's heating oil, whether it's diesel. They're all pretty much, they're carbon and hydrogen. There's not a lot of other stuff in there. There are desulfurization units, there are denitrification units. So the whole point is to get rid of some of those impurities. So it's primarily carbon and hydrogen, and it's viscosity and volatility derived. Biodiesels look at basically fatty acid esters. So fatty acid, whether it's palm oil, stearic acid, there are all sorts of different longer chain hydrocarbons that have what's called a carboxylic acid at the end of it. So it's just a CO2H. That H can be taken off in what's called esterification to make, instead of the H, it gets replaced with another carbon hydrogen molecule. So typically, there are fatty acids that are called triglycerides. So glycerin is one component of it. It's a triol, so it's got 3 hydroxyls, and it'll have 3 of these fatty acid chains coming off of it. So the whole point of making biodiesel, in many cases, is to take those kind of natural products, that whether it's from a corn plant, whether it's from sugar beets, or what else can we do to generate these biological materials that you can take the glycerol off, and you can modify these type of materials to have something that's got a pretty uniform characteristic, good viscosities. They are primarily carbon and hydrogen, but they will have double bonds, so they've lost some hydrogen somewhere, or they'll have the oxygen still associated with it. And it's all around viscosity and sort of its lubrication capability. Does it have the right volatility? And certainly some of them have a volatility that's appropriate for a diesel. Now, we talked a little bit about vapor pressure volatility. Diesel is quite a bit different than gasoline. People tend to think that, well, they're both burned in a vehicle, so they must be the same. Gasoline is burned by what's called a spark ignition engine. So it's got a spark that lights it on fire. Diesel is compression ignition. There is no spark. There's what's called a glow plug that has a heat source, or at least an ignition source, but it's all about you compress the vaporized diesel, and as it does that, as you raise the pressure, the temperature rises. And you can raise it to the point where you actually ignite it with this glow plug. It explodes, it pushes the piston down, but it didn't use the spark. Because the volatility is so different with diesel than it is from gasoline. But these fatty acid natural product diesels, biodiesels, can be very similar. They can still work in a compression ignition motor. So, but they are all essentially the same. So each of the fatty acids, it might be a C16, so it's got 16 carbon atoms or 12 carbon atoms, but they're all essentially the same. And we talked about with gasoline or just refined hydrocarbons, a diesel will still have a range of materials in it. So some will be more fluid or more volatile, others less. They don't necessarily respond the same way to a spill response. But like you mentioned with the SDS, it might give you some information, but until you actually test it, you don't necessarily know if you say, oh yeah, it's going to be just like a petroleum-based diesel, will just do the same thing. I think it's up in, around Aberdeen, Washington. Is it Grays Harbor?
Yeah, it's in Grays Harbor.
There's a biodiesel
Reg facility. Yeah.
Yes, because I know we had some concern about that, at least discussing it, because I think where that biodiesel might spill, it's mud flats, it's relatively shallow, and that could potentially be a problem. But it would have to be tested, because I know I've been asked, can we disperse biodiesel? And I have to admit, I don't know. The same thing with—
What about bioremediation?
That would actually work.
I mean, it sounds like a biodiesel would be slightly yummier for—
Yeah, and that's the misconception, that because it's a natural product, it must be much more amenable to a biological process to degrade it. But that's not necessarily the case. And the thing we actually know in the case of Macondo, with this dispersed oil in the water column, the Gulf of Mexico, if you looked at the dilution and degradation. So if you had a concentration of the oil in Gulf of Mexico, 1,000 meters down, it dilutes and it degrades, because again, there are bacteria that can deal with crude oil, and the half-life of its time in the environment is relatively short, even in 1,000 meters down. I don't know if you had a concentrated biodiesel spill, what would be its biological demand. I'm not sure. Would it degrade eventually? Sure it would, because it is, again, it's a fatty acid type material that organisms have seen for years, eons, that I would imagine it would work. But it's that fallacy to say because you stick the word bio in it, it must be so much more compatible to the degradation process. And I just can't say that I know that that's true.
So, I mean, I'm not a chemist, but I mean, the part of the goal is to concentrate the carbon and hydrogen that's in this product, right? They do some— I'm not sure, would you really call it refining, what they do with the—
in a sense it is, but it's not the traditional sort of the catalytic cracking and other reforming processes that are done in a petroleum refinery. But there are some things, and the thing I've heard, again, when you refine some of the fatty acids, especially with the triglyceride component, glycerol is a byproduct, which it's not bad. It's used in different food it's a processing agent. It's other things. It's very viscous. It has even cosmetics that can be used. But there has been at least one case that I can't remember where it was, but it overflowed into a stream, And because of its ability to degrade fairly quickly, it sucked up all the oxygen concentration within the stream, and it ended up killing a number of fish, of which some of those were a sensitive endangered species. So natural products are not necessarily benign.
What about burning? Has any tests been done for in situ burning with these bioproducts?
Not that I'm aware of, but I'm sure it would burn fine.
I mean, that's the whole
Again,
idea, right? We can still put it into the car's cylinder and ignite
Yes,
it
it
with a
will,
glow plug and compression.
And I would imagine that, again, it would probably be sooty. If you've ever had, let's say, an oil fire in a frying pan, it puts out black smoke. So I think it would probably still have to have some work done associated with it. But I haven't read any studies about in situ burn of biofuels.
That sounds like an open area of research for someone.
And I guess actually a biofuel has actually been used to fuel a jet aircraft. So yes, they're getting to the point where certainly a lot is known about their combustibility ignition processes. Because if you're willing to fly a jet on it, you've got to have pretty good confidence in that ability to burn it.
Okay. I drive a diesel. I drive a Volkswagen Golf with a diesel engine, and I have a gas station nearby that runs a B20. So it's 20% biodiesel, and I don't notice any difference in performance as I go from one to the other.
And they've gotten a lot better, because if you may remember, when the early, I'll say the Rabbit diesels came out, they were very smoky. But because of, I think, the catalytic capability, and I think the quality of the fuels, that's not necessarily an issue anymore. Because I think, again, that is a little bit too early. And now that the technology's gotten there, they're fine.
I've never had the nerve to run a B100 in it.
I don't know. It's the same thing. You can do the flex fuel cars where it's ethanol, and I wouldn't want to go to 100%. And the problem with ethanol is it's already partially oxidized. So you've given up, in my opinion, some of the energy density of the fuel that you're putting in your car, because the gasoline that goes in essentially has no oxygen, and the whole point is you're burning it. So it kind of derates the fuel efficiency and the performance. Diesel's a little bit different. It's a more efficient engine, so I'm not surprised that at 20% you probably wouldn't know.
Can you speak
about? Again, the renewability is a plus, but it has to be done in a real sustainable manner. There was work that was really looking initially at ethanol production as a flexible fuel, and Brazil was one of the places that was looked at, because a large percentage of Brazil was being fueled by ethanol from, I want to say it was sugar beets, or whether it was sugar cane or sugar beets, I don't remember at this point, but it wasn't necessarily where we would grow corn, and the corn efficiency for ethanol production is different. So again, it has to be sustainable in the environment you're using it in, and then take into account the distribution too. If you're a smaller area where distribution is not huge, that's one thing. But if you're spread out, let's say like in Oklahoma or Nebraska, that might be more of a challenge. But no, it's interesting to see what all the different fuel options can be and how to use that in the correct way.
Well, Tom, the last thing I wanted to ask you about is Bakken crude oil.
Okay.
It's got a reputation for being explosive. We had a lot of train derailments.
The one up in
Canada, right?
Yep.
And we had one in Oregon, and there was one not that long ago up in Custer, Washington. That was, fortunately, it happened in an area where there wasn't much of a population, but it also resulted in a fire. But it's gotten this reputation for being an explosive product. Can you talk to us about its chemical properties?
Well, it is a lighter material for sure. It's the exploration is different. It's not as deep. There are different components to it. The explosive aspect, I think, is it's misleading. Is it flammable? Yes, it is. In the case of the Canadian incident with this runaway train that then derailed downtown and ended up burning down a facility that had a lot of people in it, that was horrible. But it didn't, I'll say, as far as I know, again, this is my opinion, I'm not speaking for anybody other than my own awareness. It didn't explode, but it did catch on fire. And it is a lighter material, so the chance of it igniting may be perhaps easier than an undiluted bitumen. That's certainly the case. But Alaska North Slope crude, other things will do similar things. But the vapor pressure, from what I believe, especially fresher oil, is going to be higher. But it's the nature of the beast. We transport gasoline all over the place, and it's much more flammable than most things we deal with. People have no challenge going down to the local, whether it's a Home Depot, Lowe's, Canadian Tire, or whatever, to get a cylinder of propane. And we transport that around too. I'm sometimes concerned when I go get that cylinder, is that valve correct? And have I done it right? I'm not worried about crude oils and gasoline. Again, it's treating things appropriately. Sometimes these incidents that happened, there was the one along the Columbia River, a few years back, certainly the one in Canada. There were other things that led to that accident in the first place that I presume could have been prevented. But I think sometimes the Bakken crude has gotten a little bit of a mislabel. We talk about lots of things being explosive. It's like, no, that wasn't really an explosion. Let's just talk about the fact that it was a fire that got fed for too long by a source that just kept going. Personally, I'm not too worried about it. We had an exercise. It was actually a comparative risk assessment we did for a potential scenario in Philadelphia with the Coast Guard, the EPA, and others. And one of the scenarios was a Bakken-type train derailing in downtown Philadelphia. And how would you deal with that? And in many ways, you deal with it the same way you would with any other spill. It's usually evacuation, it's notification, it's response, it's being prepared, and having people like yourself and others who are aware of the challenges, but also understanding what the spill response, the incident command can and should be doing, and essentially being ready for it, not having to gear up for it on the spot. The last thing you want to do, I think we were talking, I've talked to somebody here at work recently, you don't want to be meeting people for the first time in the middle of an incident. You want to know them well in advance. So we always talk about prudently over-respond, and then you can dial it back to what it actually has to be, but assume a worst case.
Tom, you're going to be out here in Washington for Clean Pacific in August. Where we have the next opportunity to hear you actually present and teach?
Well, I have to admit, that's one thing. So again, like you said, I work for Applied Research Associates, but I am the OMSET facility manager. We're hoping to get training back here. COVID-19 has actually pushed a bunch of things back. I've done a bunch of courses here. I did the oil spill response, what we call 201 Beyond the Basics, for the International Oil Spill Conference a few weeks ago. We had 90-something people who logged into that, which, for good or bad, for COVID-19, it has allowed more people to sign up for things virtually. And I hope we can keep doing stuff like that. I've given a talk for NOAA's You Don't Know What You Don't Know series last fall it was really about some of the research we do here at OMSET. But I'm always happy to talk to people. And I'm looking forward to hopefully being part of the Northwest Oil Spill Control course again. I've done training out in the outer coast of Washington State with the tribal groups there with MSRC and the Coast Guard. I'm always looking forward to doing stuff like that. So my company now supports me doing stuff like that, even though what I'm really trying to do is keep this wave tank facility occupied. Part of that is really the outreach, because the spill response community globally is a relatively small group of people. But how do we keep on sharing the information a bunch of us have, especially since we hope there won't be too many more big spills? So people won't be getting firsthand experience, but how do we make sure we're ready for it? And unfortunately, also, we know a lot of people who are near retirement or have retired, and we're losing some of the capabilities and experience out the door. I did retire from ExxonMobile, but I have the luxury of still being involved. So I'm always happy to talk to people. And again, this is a great forum. I really appreciate the opportunity to talk to you.
No, I really appreciate you coming on the podcast. That was one of my goals in setting up the podcast, is to capture some of this information for posterity. People like Al Allen, who have
Oh, yeah.
pioneered in situ burning, who really has retired. And,
Yes.
there's not going to be a lot of opportunity in the future to have those kinds of conversations. If somebody wanted to get a hold of you for training or lectures, do you have a website or email address you want to share?
Sure. Yeah, well, actually, so you can go to you can just search OMSET and you'll find us. Again, it's the wave tank that's here in Leonardo, New Jersey. But I'm just tcoolbaugh@ara.com or tcoolbaugh@omset.com, either one. And that'll come right to me. I'm always happy to talk. On the website for OMSET, there is a phone number there for me. And we're easy to get a hold of. In fact, I just had a request from somebody down in Brazil to talk about some of the work that they're doing. And during the course that I gave a few weeks ago, there was somebody from India. There was somebody, I talked to people in Singapore and Australia. So that is one thing that this virtual format has really allowed us to expand. But it's really trying to just keep in contact with the network. And if there are questions that we can help people learn from and really get that next generation up and running, that's really the thing to do. Because, I'm not ready to retire, but there are times you sort of sit there and think, gee, why am I getting up at 5:30 in the morning again? It's just, at least I'm not on the emergency response side from the 24-hour-a-day aspect of ExxonMobile, but my phone's always on. So it's still sort of the same thing.
I wouldn't know how to retire. I mean, what would I do?
Well, that's it. Working with you guys, working with Oil Spill Response Limited, and again, MSRC, Clean Gulf Associates. Frank Paskowitz was just on a call that it was on, and it's just, we're all here. It's just, that's kind of the nature. You find out when you start doing this stuff that you kind of, you don't want to leave it behind. You kind of like what's going on, and it's a great organization. It's a great community, I guess I should say, both the responder and research. And regulatory, the fact that now I manage a facility that actually is owned and operated by the Department of Interior is quite a bit different to me. I was always the customer. Now I have to go out and find customers. It's like, okay, and help them figure out what they want to test, and we'll do the best we can. The one thing that's unique here is we've got a crew of 10 or 12 people here on site. They have been to more oil spills than probably anybody you'll meet. The spills typically are no bigger than 10 or 20 gallons, but it's out on the water. They pick it up with skimmers. We do disperse it. We just don't burn it. We've got the fluorometers. We can look at the SMART protocol approaches. We can do other things here. But it's that aspect that I get to keep on doing, the chemistry and science of oil spills. So why would I quit?
There you go. Well, I'll be asking you to come back on. We'll talk about SMART as a separate podcast.
Oh, yeah.
And I look forward to seeing you in August. Tom, thank you so
That'd be
much
great.
for your time. I appreciate it.
No problem. Thank you very much.
Well, that's it for this episode of the Tactics Meeting. That's all the time we have. I hope you enjoyed it. I really enjoyed talking with Tom about the chemical and physical properties of oil. If you did enjoy the show, please help us spread the word. Send a tweet or an email to a friend and recommend that they check out the program. I hope to see you all at Clean Pacific. Join us next week where we'll be talking about the role of the safety officer. Until next time.